Rotational motion. Let's go. This is a very interesting aspect of physics that we'll be dealing today. Before I continue, there are some certain things you should know under rotational motion. The part 1 of the video may be boring. Please endeavor to watch it. If you're not conversant with rotational motion and I'm trying to prove a formula, I will waste time proving some formulas. Why will I waste time doing that? Because they are needed. If you do not know how I got the formulas, you may find the topic very hectic, even when it's so easy. So calm down, bring out your jotter, and let's continue. Remember, for rotational motion, let me start from linear. From linear motion, remember that momentum is mass times velocity. Remember that from linear momentum. But then we are in rotational motion, and I will be changing or interchanging a lot of things at the beginning of this course. Now, what will I change? I want to first, before I continue, I want to give you a relationship between linear and rotational. I call it translational. Let me call it linear. When you are dealing with linear and when you are dealing with rotational. Once you are dealing with linear, we know that x, remember from equation of motion, that x is equal to ut plus half at squared. You already know that this x is the distance, is it not? Good. This is linear. What we're talking about linear. What we're talking about rotational is the same thing, just that the sign change. So in linear motion, whenever I write xo like this, it means the initial distance, right? And if I write just x like this, is the final distance. But under translational motion or under rotational motion, if I write something like this, the distance is represented by theta. And so since this is initial speed, this is the initial distance under rotational. And then this one should be the final distance. The same thing is happening. Remember, from V is equal to U plus AT. This is linear, equation of motion under linear. Remember that this is final velocity, while this one is initial velocity. Is it not? So I can actually come here and write V0, V, while I can say this is my initial velocity and this is my final velocity. Is it not? Good. But under rotational, we are actually representing this V as angular velocity. So this is comma, let me put comma here, and this is the final angular velocity under rotation. The same thing applies. Remember, from V is equals to AT here, right? Here is the acceleration, the A is the acceleration, right? I want to represent it with the capital A because I want to write something here. The A is the acceleration. Under rotational, acceleration is an A like this, small letter A, this way. Note this things. I'm wasting my time because if you do not understand this, believe me, the course will be boring. Now, remember from equation, second law of motion, F is equals to ma. You know this formula, right? This is from linear. I'm wasting my time to explain this. That formula is from linear. And remember that this m is the mass, is it not? Good. So under linear, M still remains the mass. Under rotational, you don't write M, the symbol changes. It's no more M but I. This is the bump. Start writing it down immediately. I want to resolve this course immediately. Under linear, this is a capital M. Under rotational, we change it to put I. So we replace M with I under rotational. Remember, I said that momentum is product of mass times velocity. Is it not? Good. And under linear, momentum is P. Under rotational is L. They represent it with L. So under the course of this topic, if I'm writing L, don't say where is this coming from. If I write I, don't ask me where is it coming from. I represent the mass. The L is the momentum. Remember from here, from second law, Newton's second law, that F is equal to ma. So under linear, the force remains the same, which is F. Under rotational, the symbol of force changes to torque. The symbol of force changes to torque, and that is how to write it. Good. Now let's continue. Remember, this is introduction. Now, the same thing is happening. From the above equation I just wrote, if I already said that the momentum is mass times velocity, and whenever I write it like this, that means I'm talking about the linear form. If I want to represent it right now, rotational form, this formula will now change to L is equals to I W. If I write it like this, that's what I'm talking about the rotational form, because P is equivalent to L in the rotational, M is I, and this is the angular velocity. Did you see why I'm wasting my time to explain this? Good. Let's continue. Now, I want you to know something. This mass, which is this I, right, is called the moment of inertia. Write it down, the moment of inertia. And the moment of inertia, it comes with a formula. Write it down immediately. The moment of inertia comes with a formula which is capital M R square. That is the formula for calculating the moment of inertia. Capital M R square. I want you to know something. I'm proving formulas one after the other. Write it down. You get why. Now, if I should call this my equation 1, call this my equation 2, call this my equation 3. Now, listen, there's something that's going to happen right now. I want to carry this. Now, remember, under my channel, I gave you a formula when we're dealing with simple harmonic motion. I said there is a formula that relates linear velocity to angular velocity, and that is this formula, that V is equals to omega R. Let me call this equation 4. Of course, you know this is linear velocity, this is angular velocity, this is radius. Now look at what I want to do. I want to make the angular velocity the subject of the formula. So this will now be V all over R. Let me call this equation 5. All this formula, we'll use it for calculation. So you better open up your mind to understand this. It's so easy. Now, if this is my equation 5, now look at what I want to do. Look at what I want to do. I want to put equation 5 and equation 3. I want to put it into equation 2. And equation 2 is L is equals to I omega. So, and I already know what is my I and omega. So, L is now equals to, my I is capital M R square, while my W is, let me do like this, V all over R, right? This is another equation. Let me call it equation 6. Now look how it's going to happen. This R will cancel this R, right? So the rotational momentum will now be capital R, capital M, right? R and V. Now I want to make this, I just want to readjust it because I want to collect something here. I can just write this, L is equals to capital M V R, and let me call this equation 7. Now notice something from equation 1 here. Notice something there. I told you from 1, P is equals to mass times velocity. And so this is mass, this is velocity. So I want to remove this and replace it with P. Therefore, that means that your L is equals to PR. Now, this is equation 8. Under the course of this topic, we will be doing a lot of calculations. So there may be a calculation. I'll give you the moment of inertia, I'll give you angular velocity, and I ask you to calculate the rotational momentum. So you can use this equation. But what if I just come here, I give you momentum straight, and I give you the radius? You can also as well use this formula to get it. Then what if I give you the mass, the radius, and the linear velocity? You can also use this other formula to get it. That's why I'm wasting time. If you do not know how we are getting all these formulas, it will confuse you. Now let's continue. We'll do a lot of derivations in this first part 1 of the video. Let me even write it. This is the part 1 of the video. Now let's continue. From Newton's second law of motion, believe that we have copied this. From Newton's second law of motion, we know that force is mass times acceleration, right? But let me call this equation 9. But acceleration is change in velocity all over time, and let me call this equation 10. Of course, acceleration is velocity over time. So I will put, wherever I see acceleration, I will remove it and put change in this over this. So F will now be capital M, change in velocity all over time. Now notice something. This is equation 11. We can use this to solve questions. Now look at this. Remember that P is equals to mass V. So here already is the momentum, linear momentum. So I'm going to remove it and replace it. So your F automatically changes to P all over changing T. This is another formula to calculation. This is another formula. And if you are actually very good, you will know that if you change this from here, if I cross multiply, you will now see that this is F changing T, which is equals to P. And this is the formula for impulse. If you still remember your O level very well, this is the formula for impulse. Now, I'm taking my time to prove all this formula. We have not even started proving under this part 1. We will prove and prove, but you enjoy it. Now, let's continue. So we have gotten that formula, right? Good. Now, let's enter what is torque. I just introduced torque to you. Remember, I want to clean this side, believing that you're copying it down on your notes. From Newton's second law of motion still, M is equals to MA, right? And then remember, I want to talk about torque. We are under a topic now called torque. And you know the symbol. Now you know that torque is, I want to change everything to rotational. F represent this. This will be what? I, right? I hope you are not forgetting. Are you with me? Good. So what is the formula for A? This is linear. let me use this thing so that I will not be confusing. Let me use this thing as the angular acceleration. This is the angular acceleration, rather than using capital E and small a. Now, pay attention very well. I still want to drive. Now, this is the angular acceleration. And angular acceleration is, remember, here will not be I. Angular acceleration is changing omega all over time. The same way the linear acceleration is changing v over t, angular acceleration is changing omega all over time. Remember, this is torque. Right? Now, look at this thing. There is a relationship there. Can you get it? Yes, I proved that before. I proved to you that L is equals to IW. So if I should replace this whole thing with L, torque we have, this is not T, this is something like this. So torque will not be, all this will not be the angular momentum all over time. So it means that, let me also be including change here, change in this place. Now it means that torque is equal to angular momentum all over time. That is another equation on its own, and let me call it equation 13. So if you are conversant with this formula, believe me, any question they bring, you will solve it extremely well. It's so easy. Let's continue. Now, under this part, I've been wasting time to make sure you understand a lot of things on this topic. It is what it's entailed. Over the years of teaching this topic, I noticed one thing, that students find it easy if I finish explaining this formula like this. If not, you'll be cramming what you don't know. Now, at the end,